So check out the bubble. That's one. I mean, we're going to copy just two. For our purposes, I actually didn't think we needed a ton of different shapes. And so I have one that's kind of flattened and one that's just a sphere. Most of the shaping is going to come from deformation anyway. So that's all that was needed. So yeah, my best work ever. So those are being copied down here, and we'll get into that in a moment. But first, since we are deforming these, one of the ways we can get variation is by making sure that all of the points are not are all randomly rotated on the y-axis. And we're going to do that just by setting a quick an orient attribute. And this, rotation matrices is a big subject, and I think Houdini School is probably going to cover that, or has, right, Deborah? So for our purposes, we'll just kind of cover it in brief. I'm making a very simple orient attribute. So for those of you who aren't familiar with orient, it's a built-in attribute just like velocity or CD, or that points can read, and it's the best way to set rotations. But it takes a quaternion as input. So what we want to do is we want to set the rotation in degrees, because that's what we work in, and then convert that into quaternions so that the orient attribute can read it. And I'll just briefly run through these lines. First off, just getting a random value based on the ID of the points, so that they're all have a different value, and multiplying that by 360, because that's how much we want to rotate them. Bear with me. And then we're taking that and creating a vector called R, where the rotation of X and Z is 0, and the rotation of Y is randomized around 360 degrees by this previous line. Next, since this function right here that gives the quaternion, this creates a quaternion for orient, it needs a value in radians. So the first thing you can see is we're using a function called radians to turn those degrees into radians. And then that's enclosed in this function called Euler to quaternions that then creates the quaternion that orient can use. And this last bit here just tells it the order of rotation. So if we go to the spreadsheet here, we now have an orient attribute. And it doesn't make a whole lot of sense if you're used to working in degrees. But that's giving us our randomized rotation in Y. All good? Anything before I move on? I'm actually going to illustrate what's going on with that, because we'll go over this copy to points loop in a moment, but no orient. I'm just copying some cones to the points right now. By default, they will point in the direction of their velocity, and that's not what we want. So the orient attribute will override that. So put that on, and you can see it's all randomly rotated. Okay, questions?
We had a question from Mick about, it seems like you put the up vector and the degrees in one line. This is axis and spin, right? This orient, yeah. So the X form XYZ is the order.
The order of rotation, as I understand it.
Ah.
Yeah, as I understand it. It's possible I could have made a mistake here too. So, but if you change this to, it does appear to be working, because if you change this to 45, oops. then it will only rotate them on 45 degrees or
Mhm.
90. Excuse me. But there might be a, 1 second, please. Apologize for that. Yes, there's possibly a better way of doing this, but this seems to work for me. And I actually have a lot of HDAs that let you set randomized rotations in general directions that are very handy. All right. So let's just get to the copy to points here. So next, we want to set a few attributes that we can then reference on these points as well. And one is we're calling offset. This is going to be offset to a noise, a deformation that we're going to use. And we're setting a random value based on the ID again, and then adding the age of the particle to give it some motion, and then multiplying it by a rate, by a parameter that we're calling rate. And these will all be read by the points downstream. And then this is a bubble index. This is just, we can reference this in a moment. I'll show how we're doing that. Taking a random value and multiplying it by 2, then turning that into an integer. And if we look at the geometry spreadsheet, what that gives us is an index that's 0 and 1. It's the value of 0 and 1 that we can use to switch between the two bubbles that we've created. So this copy to points loop is some of you might remember the old method of doing copy stamping. And this is a better way of doing it. In fact, I think copy stamping has been deprecated. You can't use it anymore. What this does is it's rather than copying all the geometry at once, it does it in a loop to every point, one by one. It loops through all the incoming points. And it also, you're able to inherit any attributes that come into those points. Along with that, in a method that actually is, to me, very similar to copy stamping, you can reference point attributes before they're copied onto the points. Or actually, yeah, reference point attributes that are back onto other SOPs, in this case, the bubble deform. So what we're doing here is we're using a point function, which grabs point values or attributes. And we're looking at this, the first node here, this for each begin. So the input of the loop is going to grab the index and the offset attributes that we created. So in the bubble deform, at every frame, it will look at that point and copy the offset into, excuse me, 1 second. Recently recovering from COVID, so I'm still a little bit congested, so I apologize.
You're doing great.
So this then gives a per point offset for all the bubbles so that deformation is different for each one, and it changes from frame to frame. In the same way, in this switch right here, we're referencing the index to switch between the two inputs, bubble 1 and bubble 2, to vary the geometry. So does that all make sense? So downstream from that, we have much more interesting bubbles. they're have some initial shape, and then this attribute noise is deforming them, and that deformation is varying based on a randomized value of the particle ID from the particle ID, and updating it every frame. So should probably make a, yeah, here we go. So this is probably a little bit jittery on your screens, but you can see you've got some, especially with some of these particles here, you can see as they move upward, they deform. Any questions on that so far?
Any questions? I think just compliments. Looks good.
Yeah. Okay. Downstream from there, we're going to split them again. So stream first input, meaning we can split out the broke something. We can split out the bubbles that are being spawned from the growth source, and we can split out the ones that are spawned from the flip later on. There they are. So, yeah. Next, the next thing we want to build is, as you can see, the bubbles all have a little bit of trailing particles. So we want to have a little bit of, and in fact, when I ran this render last night, I wanted to double check that the file was working for everyone before I gave it to you. A couple of things I noted is those trailing particles could be a little bit larger, and even the burst particles here could be a little bit bigger. They might have actually been in the original file. That's easy to adjust. So, all right, let's do those trails. Super simple. And you'll see why these are split out into two later on. All right, so let's copy and paste that. Merging them back together because we're going to use that geometry to source some points that there'll be the trailing particles. So if I dive inside here, there's not a lot going on, really. Once again, the main difference is for the first time, we actually are scattering onto surfaces. So, and again, just like everything else, we're referencing our global bounds. Make sure that this pop advect, yeah, it's looking at our pyro to advect. And if I run forward a little bit, you can see source, the source geometry coming in, and spawning particles. The trick is that I think some of them are coming in very fast and shooting off in different directions. And that's where pop speed limit comes in handy to just calm everything down. Other than that, we didn't want a whole lot of initial velocity because we want them to be trailing. So we're just getting 0.15 of the velocity of the incoming geometry. And that gives us our trailing particles. So, and again, I'm adjusting their p-scale outside of the simulation. So if we...
What is the lifespan of those particles?
Oh, again, fairly arbitrary. They're, yeah.
Cool.
Half a second with a variation of a quarter of a second. So let's see. Template these. I'm just going to do a quick So building these kind of effects, multi-layered simulations, it's really, to me, about this. It's about having variation in sizing and behavior on the different particles. And bubbles are a good example, but you can really apply this to a lot of natural phenomenon. And as you layer them together and um, give them individual motion, you can create a lot of complexity very quickly. As you can see, there's not a whole lot like this setup isn't terribly complicated. It's just feeding one simulation into another and using a lot of advection. Um, I also did a thing early on that was kind of fun where you can create an airfield with a pyro solver and use the bubbles to perturb that velocity field. And that's pretty fun because then you can actually have the trailing bubbles or the bubble bursts taking on the velocity or reacting to the velocity of the bubbles as they move. It ended up being a little more complicated because you get in order of, in what order do you run these, and you can't, you'd have to break that out as a separate process to run the bubble simulation, then feed it into pyro airfield, and then use that to advect. But it does give some fun effects, and I would totally give it a go if you'd like. So this is the let's see, do I have a, was I making a, oh, there it is. Yeah, so here we have our, yeah, preview. So some fun motion. They're lagging a little bit and behind the main bubbles, and getting some nice swirly motion from the advection. So yeah, I think at this stage, those are all the simulations. Now, really, it's about how we bring that all together. And is there any questions before we jump into that?
We do have a question about the Part4 still, but I feel like we can leave that to the end when you're
Okay.
totally finished. Yeah.
Okay. All right.